Hello guys again. So today we'll start another chapter which is about acid base and solubility equilibria. So in this chapter we're still in equilibrium, and that means that you should still know up to now the conditions requiring the equilibrium, as well as some of the factors that affect equilibrium, since we will also deal with the effect of concentration later on. So we'll start with chapter 16. So we only have the three topics allotted in this chapter 16. Note that the 16.3, which is buffer solutions, is included in chapter 15. So we all have these three topics. First is the solubility equilibria, then a common ion effect and solubility, and last, we are applying this solubility equilibria with the common ion effect to separate ions by using fractional precipitation method. For the objectives, so at the end of this chapter, you should be able to know the solubility rules, interpret solubility product constant in terms of solubility and molar solubility, calculate KSP from solubility or molar solubility, and last, predict common ion effects on solubility. So as you can see, we all have solubility in all the objectives. Okay, let's start with 16.6, solubility equilibria. So from Gen Chem 1, we know already different types of reactions, and one type of reaction is that when we have an acid and a base, for example, it will react to form a salt. Okay, so some salts are solids, so that means in the reaction, the the salts become solids and it precipitates off in the reaction. So we call those reactions as precipitation reactions. And these reactions are important in everyday life. So we have precipitation reactions occurring in our body. We also have precipitation reactions occurring in the industries, in the medicine, for example, to have products or medicinal products and industrial products. So we need precipitation reactions. Okay, so note that the solids that form after the reaction, so we call that as precipitates, and these precipitates, since they are called precipitates or solids, these are not very soluble in water or in the solution wherein we have the reaction. So we call this also as sparingly soluble salts, or not very soluble salts. Okay. So if we have the precipitation reaction, if we reverse that reaction, it means that we are going to dissolve these precipitates or these solids. Okay. So that means that there may be an equilibrium reaction involved in performing a precipitation reaction, since the backward reaction, the dissolution of these solids, can also happen. So how do we know how much this sparingly soluble solids is dissolved in water or in a solution? So we have this solubility equilibria. Okay, so just to have a recap on whether the solid is a sparingly soluble or insoluble salt or not. So please take a look at this table. So I hope that this table was shown to you, or you should be able to know this the contents of this table by now, since this is given on Gen Chem 1. So for example, we have compounds containing lithium, sodium, potassium, rubidium, ammonium, and cesium. So they are soluble compounds. For example, we have sodium chloride. we have sodium sulfate, we have ammonium chloride, potassium sulfate, and lithium nitrate, cesium nitrite, for example. So they are soluble. As well as the nitrates, bicarbonates, and chlorates. For example, we have sodium nitrate, sodium bicarbonate, sodium chlorate. They are soluble. For this, we have halides, we have the chlorides, bromides, and iodides. So they are soluble compounds except if we have silver, mercury 1, and lead 2 ions as their cations. So for example, silver chloride is insoluble. Silver bromide is also insoluble, as well as silver iodide. So the same goes with the sulfates, but we have also the exceptions. So we have many exceptions for sulfates. And then at the bottom part, we have the insoluble compounds. So that means, for example, we have calcium carbonates. So calcium carbonate is insoluble compound, or calcium phosphate, or calcium chromate, or calcium sulfide. Okay, but there are exceptions for this. So we have alkali metal ions. So for example, we have sodium ion. So we have sodium carbonate that is soluble, sodium chromate, sodium phosphate, sodium sulfide. So, or we have ammonium ion, ammonium sulfide, ammonium carbonate. They are soluble, and as well as these hydroxides. Okay, they are insoluble except for the alkali metal ions, such as again sodium, potassium, and so on, and the barium ion. Okay, so knowing this, so we can see whether a compound is soluble or not soluble, or insoluble in water or in solution. Okay, so going back to the study of solubility equilibria, for example, we have silver chloride. So silver chloride is an insoluble or sparingly soluble salt. Okay. So the solubility equilibrium reaction is given. So silver chloride. Okay, so this will be dissolved. So that means we have silver ions and chloride ions. But take note, not all of the silver chloride will be dissolved since it is insoluble in water. Only a very, very small part of the silver chloride solid is dissolved in the solution. Okay, but still we have these ions. Okay, so if we are going to write the K, or the equilibrium constant for this reaction, so it is only the concentration of silver ion times the concentration of chloride ion. So again, we do not write this solid silver chloride since it does not change its concentration abruptly. Okay. So let's have a definition for the solubility product constant, KSP. So the KEQ from the last expression, so that is also called the KSP. So SP stands for the solubility product. So this is the product of molar concentrations of the constituent ions, each raised to the power of its stoichiometric coefficient in the equilibrium equation. So this is another type of KEQ, but this time the KEQ is for the dissolution of the insoluble salts or insoluble solids. Okay, let's have a problem in writing again KSPs or KEQs. So please write the solubility product constants of the following solids. Again, pause this video and then write the KSPs, and then let's check later if you have correct answers. Okay, so let's have this. Okay, for magnesium fluoride, So I have given you the names. So that means you have to first make it into its chemical formula before proceeding with the reaction, then finding the KSP. So magnesium fluoride is MgF2. So if MgF2 is dissolved in water, it will form Mg2 plus and 2 fluoride ions. So the KSP is the concentration of magnesium ions times the square of the fluoride ions. Next is we have silver carbonate. So this is the silver carbonate, this solution. So the KSP is equal to the square of the silver ion concentration times the concentration of carbonate ions. And then last, we have calcium phosphate. So again, this is the dissolution reaction for calcium phosphate. So the KSP is the cube of calcium ion concentration times the square of the phosphate ion concentration. So I hope that you must remember the names as well as the chemical formula for cations and anions, so that will be the first requirement to get the dissolution reactions before finding the KSP equations. Okay, moving on. There are two ways to express the solubility of a substance. So again, when we say solubility, okay, it's like a concentration of the solid in the solution. So first, we can have molar solubility, which is the moles of the solute in 1 liter or per liter of, take note, a saturated solution. And then the next is solubility, wherein we have the grams per 1 liter of a saturated solution. So take note that in getting this solubility, we have a saturated solution of the solid. So that means when we have saturated solution, we have the maximum amount of the solids that can be dissolved in that given volume. So here we have both 1 liter. So again, solubility is in grams, molar solubility is in the number of moles. So this is like molarity or the mole per liter. Okay, so how do we get this KSP? So just like in other equilibrium constant expressions or KEQ, we are using molarity. So that means we are going to use this mole per liter, or we are using the molar solubility in finding the KSP. Okay. Let's have a problem regarding this. The molar solubility of calcium sulfate, so I already gave you this formula, is found to be 0.0049 mole per liter. Calculate the value of the KSP or solubility product constant for calcium sulfate. Okay. So in this one, so I'll give you a hint. So you'll need first an ice table. So again, just like in any problems dealing with equilibrium reactions, and then find the KSP expression and then get the value of this KSP. So again, please pause this and then try to recall all the things that we had done in chapters 14 and 15 and then apply it here. Okay, so let's have this simple solution. Okay, so we have the calcium sulfate. So calcium sulfate, okay, so the dissociation for this, so we have 1 mole of calcium ion and 1 mole of sulfate ion. So from the ice table, we do not write any concentration for the solid. So initially we have 0 mole or 0 molar for calcium ions and 0 molar for SO4 2 minus or sulfate ion. So the change in the concentration, we can let it as X, or this time we will use S as the molar solubility. Okay, so you can write X or you can write S. But most of the books that deal with this solubility product constant, they use S, small letter S, for the molar solubility. So the equilibrium concentration is 0 plus S, so that is S, as well as for the sulfate ion. Okay. So getting the KSP expression for the dissolution of calcium sulfate, so we have the concentration of calcium ions times the concentration of sulfate ions. Okay. So the concentration of calcium ions is S. The concentration of sulfate ion in equilibrium as well is S. So that means KSP is equal to S squared. Okay. So this S corresponds to the molar solubility of the calcium sulfate. So it is given on the problem. So you'll just plug in 4.9 times 10 to the negative 3 and then square that, so you'll get the KSP, which is equal to 2.4 times 10 to the negative 5. Okay, so again, KSP here is just like any other KEQ which has no unit. So even if we have S or the molar solubility with the unit mole per liter, so we do not have unit for the KSP. Okay, another problem. Okay, so this time you are given the KSP and you are required to calculate for the molar solubility of copper 2 or cuprous hydroxide. Cupric I mean. Okay, so let's have this solution. Okay, so we have copper 2 hydroxide. So if copper 2 hydroxide dissociates, so it will give off Cu2 plus and 2 moles of OH minus. So again, we'll use the ice table. So we have the initial concentrations for the ion, so we have 0. And then after dissolving or after establishing an equilibrium with the solid, so copper 2 plus will have plus S and the hydroxide ions will have plus 2S. So again, 2S, since we have 2 moles of OH minus from 1 mole of copper hydroxide. Equilibrium concentration for copper 2 plus is S, and the equilibrium concentration for the hydroxide ion is 2S. So KSP for copper hydroxide is equal to this equation. We have the concentration of copper 2 plus times the square of the hydroxide ions. So plugging in this equilibrium concentrations to the KSP expression, so we have S times 2S squared. Okay. So solving this will give you 4S cubed. Okay. Rearranging this KSP is equal to 4S cubed so that we can calculate for the S or the molar solubility. We get the cube root of KSP divided by 4. So plugging in the value of KSP, okay, so we get 1.8 times 10 to the negative 7 molar. So this time we have the unit for the molar solubility, molar or mole